Hello, this is Alok here. So today we are going to talk about data and analytics strategy from the industrial perspective. And we have seen that now digitization and industrial IoT are sort of have become synonym to each other, and hence it is important to understand how these two strategies affect the digitization. So today, when we look into the industrial information world, it's pretty disconnected. And I try to just picturize it in two ways. One is more from the vertical systems, how it is being built in the past. So if we'll start from on the left-hand side, you have a lot of production processes, whether they are mechanical, chemical, electrical. So you're talking about refineries, you're talking about the manufacturing plants and all of that sort of. You have tons of machines, sensors, actuators, and all that. And then you have the sensors and controls which is put on top of those environments. So that is basically you are trying to automate these processes and with the least human hands. The third layer which comes in is the monitoring and supervision and automation. So this is SCADA layer, where you are put your regulatory controls so that you don't mess around against the safeties and others, and try to create a history out of it through the historian. This is where now you're getting into a little bit crossing the chasm and going into the different world, which is operational processes. So this is where you will now start talking about the information driven or IT driven systems, where you're looking into ERP and logistics and all those kind of stuff. And then you get into the business processes, which is like order management and other kind of systems. And each of these has its own sort of layers, and the other way, if you look into, is more flow perspective. That's like on top you see that you can start from staging, which is like you procure different raw material, you do the staging, setting it up, and then your core process starts. Like you start whether it's a core process is refinery, then it's a chemical process. If it is a manufacturing, then it is a manufacturing process. And then the last stage is more a distribution, where you are putting everything together, assembling it, preparing and packaging it, and ready to get distributed through different mechanisms, and that's where the logistics play. Now, the issue with the current architecture, which is historical architecture, is that your controls are event-oriented and they are not necessarily compatible with structure-driven operational systems. Most of us who come from the IT background, we all understand the importance of the information systems or information models, like how important it is to drive the logic of the enterprise. On the other end, when you look into these controls, they don't have the capability to maintain the information. They are pretty much driven by the flows and like pipes and boxes, basically, what you can say. And hence what happens is that the end-to-end the processes need continuous linkages to people. So like when people you make a model rich environment, which is upper layers, and then you on that you provide that intelligence or insight to people who will change the underlying infrastructures, like through either changing the control system or changing the MES kind of systems. And that's a current environment which we see in the industrial. And the problems which they originated because of the way which we layered this whole system. So like we layered into the control systems, SCADA systems, MES systems, and then the inventory management and logistics, which is more information driven systems, came in, and then you have business systems. And this is where we see that the lower three layers up to MES is very much like a flow driven architectures, and as you go up, it is very much information model driven architecture. The other critical difference is the lower level is driven by the assets and controls, which is more autonomous in nature, and the above is more driven by people and processes, which is more managed. And that's how we basically wrote the software. So like when people put any information, they're always putting information against the structures of the information, where machines are not same. Machines are just basically, they are either receive the message or they're going to send the events. And hence because of this, the people always are required to fill the gap. If you try to solve the problem through the flow create, and this is where basically a lot of I'll say current we see in the IoT space, where people are trying to create a sequence driven logics, which basically you start from the machine and sensor, you retrieve the data, and then you go into the what, depending upon what event or what message you receive, what will be its implication, and create a scenario based systems. The issue with that is that as you go from the layer to layer, you basically miss the context. Like the moment message leaves the machine, that message has no context which was going on in the machine. As it leaves the control system, you have no information on how that message was originated from the underlying infrastructure. So those are two not necessarily the right ways to solve the problem. So before we go into then what we need to care about and how we need to solve the problem, it's important to understand what is the anatomy of the source data. So there are two parts which we talked about. We talked about the machine-driven data, which is OT of the world, and the people-driven environment, which is IT of the world. The OT side of the data, the two things are most important: what time, what data is generated, and at what location, like what was the location of the data which was originated. And those are two important dimensions, and hence that cannot be undermined, because, and then we'll talk about a little bit about why time is important. And it's a high velocity, because these are the machines which are continuously generating data, and there's unstructured, noisy a lot of times, because not every message which comes out of the machine will have the right context. On the other hand, when we look into people-driven systems, the data is very structured. Like they have the entities, they have attributes, they have relationships, and people are forced to provide the data into that structure. Now, obviously, we will leave the collaboration-oriented tools, a little bit of social media-oriented tools in separate category, but here we are talking about the enterprise systems, which is like where most of the IT today stands. And here with the two most important dimensions of the data is the structure, because each of them, as you mentioned, that we have it, and then we have the relationships, like we have invoice, it has relationship with the purchase order, has relationship with the customer, and all these relationships are important to understand what that data means. It is structured, low volume, so it is not like you don't necessarily see a high frequency data getting generated. And it's always accurate, because there are enough filters are put so that when people put the data, that always gets scrutinized before it gets settled into the system, and it makes sure that your data is that it doesn't have any noise, and it's a right structure. Now, with this anatomy, what we have seen is that industry has tried to take or accepting this dual data architecture, like the what we call as Internet of People oriented data structures and relationships oriented, which is more driven by information models, and the other side of the data, which is more time series data models, and more driven by streams and flows. And accepting that basically has the limitations which you produce in the digitization or industrial IoT, because you're solving the problems in the old way, just that now you have become more efficient. So now you have the more data you can collect, you can do a lot of analytics on top, but you're still getting disconnected from the information or IT environment. And the whole purpose of digitization is to bring this together and create a new avenues of optimization in these two spaces. So creating a dual data architectures in your enterprise, you surely see that it's a short-sighted decision and generates very low value or ROI for the enterprises. And that sort of brings like what was the promise of the older technologies in this space, because that's always, history always teaches us a lot. So if we look into SCADA architectures, this is what SCADA was originated to solve that problem, to basically fill the gap between the IT and the OT of the world. But because SCADA was driven from the control systems up, they took the approach of the I'll say the flow oriented or control oriented. Hence, they missed the whole structural information behind, and more focus on the time series based data structures, which is historian kind of environment. And hence the outcomes were also very limited, which stopped at the historical analytics, which is based on tags or based on patterns, which sort of you can only go up, make more decisions, but when it comes to applying those decisions, you still have to rely on the people, because there's no once you create a historian as your plateau, it breaks the execution environment into two spaces. One which is running on your critical infrastructure, where you have control systems, sensors, actuators, and all that, and then what you have on the other side, on the IT side, which is more driven from the information. So that's important to see why SCADA architecture failed to fulfill the promise what they had. So what that basically brings is what's the solution, and that basically comes down to the merging of the structures and flow is must for digitization. Because if we don't understand the problem and not try to solve it in the right way, then we will be basically solving the historical problems in the new in the same way, and getting very limited results out of it. So which we see is that you have to take the models and abstractions which have been achieved on the IT kind of systems, and the streams and flows which are necessary of the OT kind of systems. You have to merge them together and create the structures which can cater to not only structures and relationships, but cater to time and location. And time means that it's important the temporal aspects of what events is generated when, what is the sequence of events, and location is important, that you're where the event is really got originated, because that affects the whole the current state of the industrial world. So we have to make sure that when we're going into the structures, we don't leave behind the time and location, and hence we will talk about what the digital models means. So from digital models, there are multiple things, but I'll talk about a few things. First is the data abstraction and structures are important, because if we cannot take your physical infrastructure, and let's take a specific example, motor. If I cannot model the motor in the way it functions in its process, then I cannot necessarily write a business logic which uses that motor. So it is important that we should be able to model it. But at the same time, if I continue to take every aspect of the critical infrastructure and move up as it is, it becomes too complex. So I'll take a very simple example. I have temperature sensor on the bottom, and if I continue to take the temperature sensor as it is all the way to the business logic, then it's too complex of a system for any developer or any user to use. Which means that abstraction should allow us to leave the details behind. And in this case, the temperature sensor may be giving you the temperature of the let's say of the pipe at a certain segment, or it may be giving you the information about the fluid temperature on certain height of a tank. And that's the information which is useful, and that should continue. But whether it is temperature sensor and what type of temperature sensor, that is not important. The important is basically what the function it is playing in the domain, and that should be preserved. And that's where we talk about the abstraction. And in that, now as the temperature is changing, that should affect the domain models or the business models, so that the connectivity between the underlying sensors and actuators is not lost with the models or digital models which may be sitting on the upper layers. On the same time, if the application makes a logic decision that I want to, let's say, again, I'll take same example, tank, that I want to change the temperature of the tank, you should be able to take that action against this model without knowing which heater should be turning on at the critical infrastructure level. So that abstraction should allow, the system should allow to do all these translations and not let the user bog down by keeping all these relationships and all these information on their height. The other thing which digital models have to incorporate is the process and flow, because we did talk about that how important is the time aspect or the sequence aspect between different events which are coming in, and how important it is the flow in which it flows from model to model from the device to device or process to process. And that means that it has to incorporate the event-oriented environment and continuously map into the structural models. And at the same time, any change of the structural models have to create the events to incorporate that impact on the physical environment or the process environment. So those are the two aspects which need to be merged in the digital models. And I'll take a very simple example just to rethrust on the point of why the time and location awareness are important. So just take a simple example that like if you have a sensor which is put on the door, and you have the counter which is looking into the people, how many people are entering or exiting from a particular hall, depending upon in which what is the sequence, like if door closes before or after a person leaves, makes the person locked inside or outside. And this is a example where very simple, but the sequence makes all the difference, that how the system will create a reasoning that is it the like depending on which event comes first, it will make a different conclusions. And that's where the temporal awareness is very important for these models. The other is location awareness, and this is a simple example. If you have a camera which is put on top of the door, and it is looking into the people, depending upon which direction it is putting, it may be computing the people who are moving, who are leaving, or who are entering into the hall. So just the direction of the camera, and that will totally change the information which can be computed from that camera. So it is important that the location awareness is captured in these models. And then you always have, like, as these like structures, and we talked about the structured relationships, which means that now we are looking into the 3-dimensional, or I'd say even 4-dimensional the data structures, which are not only maintaining the attributes and behavior, but in addition to that, it is maintaining the geospatial location and the temporal. And temporal, not to undermine it with the timestamp. The timestamp is nothing but it becomes an attribute. But in this case, you are basically continuously, your models have to incarnate depending on what events are coming in and if what sequence is coming in. So you may have a different multiple instances of the same model in different time or in different locations. So that's why it is important to bring it at the level of data structures. So what is the purpose of these data and analytics strategy purpose? Like that's because sometime, like we talked about the world of OT, which is driven by the time and location and the flow oriented and event oriented, and the world of IT, which is driven by the relationships and structures. Now, the purpose to bring this together as a part of digitization is to basically create a seamless architectures in the enterprise, which can go all the way from device and sensors and actuators to the business systems. So like this is what we're talking about, like sensing and control at the lowest level, monitoring, diagnostics, analytics and prediction, decision and automation, and then optimization. Which means that you cannot necessarily, if you cannot create a logic at any level and impact the underlying processes or underlying controls, then basically we fail in terms of the digitization, because of as you mentioned, the whole purpose of digitization is to bring a new level of optimization and automation in the industrial world. So few strategies which we need to talk about from data perspective. The first is the data process strategy. So data process strategy is basically, we know the data is going to be enormous. It's going to be continue to be originated from the machines. And the first is that, and I'm sort of starting from bottom up. The first is how to do the event processing, acquire the data, shape it, and move up by cleansing it, filtering it, so that you don't have the noisy data, and then map into the model as soon as possible, so that you have the digital models which are always reflecting the current state of the physical environment. And then now we can start about the states. We can talk about the subscriptions and rules. We can talk about orchestration, automation, process management, reporting, everything about that. But once you have the models which are reflecting the current state of the physical environment. On the other end, as we mentioned, that if change happens either because of the system or because people make a different decision at business level, it should be able to trigger it down at the same path and go all the way to the affecting the controls or affecting the actuators. And the theory here is basically to consume the data as soon as possible and as close to source as it can be, which means that the whole strategy of that take every bit of the data and put it into the cloud is not a strategy which we see that will generate a right amount of ROI for any company. We need to make sure that we take any data which comes in and consume it, which consumption means that the data becomes something. And that something is, in this case, is models, because models are the one which is reflecting the state of the physical environment. And then in the process, you may have the inline analytics, which means that you may have the continuous analytics, which is looking into the data in the models and optimizing or making different decisions. You may still have the offline analytics, because there's always going to be the analytics which need to be at the same time window as the data is generated. And you may have the long range analytics, which may collect the historical information, do analytics, make some insights or decisions, but then bring it back into the same process, because that's important. That if you bring always people in the middle, then your whole purpose of automation is lost, and you get all the historical issues. So the key is that when you have the analytics, that should be closed loop. Closed loop means that you are continuously learning, you're continuously optimizing, and you're continuously updating the processes or the fabrications or the manufacturing as it is happening in this architecture. The second comes out data storage strategy. Now, data storage strategy, I think we have been for last decade, we have been living in the big data environment, and it has been talked a lot about unstructured big data. Now, we have to recognize the industrial world is not like social media. Like social media problems are very different than the industrial world. In the industrial world, is more closer to, I would say, the managed, more like an enterprise environment rather than social media environment. It's not collaboration. It's very structured. Everything is very structured. What happens in your OT environment. Hence, we need to make sure that as we move up starting from the sensors, which surely will come as more like unstructured data, but how fast we can turn into a structured form, and then the accumulation and aggregation continue to happen in the structured form all the way to big data, which means that now you have structured big data, you don't have the unstructured big data. Because and you can see currently like a lot of analytics which we are doing in the industrial world is basically taking the unstructured data and trying to figure out what structure was really there. So instead of doing a post-processing and trying to find the structures, it's better for us to maintain the structure from the beginning itself. Like when you have a manageable environment, you as the sensor data comes in, you exactly know which sensor and what is the impact of the sensor into your digital model. So map it then and there, rather than waiting for the data to generate enormous historical data and then trying to figure out what exactly the structure, what was the purpose of that sensor was. So store data as long as it is of use, no more and no less. Very important, because just storing the data for the sake of storing is no value. It's only have cost. And hence, when we take this approach where we continuously measuring what data is important, where it is important, and once the importance is lost, then basically that data is no more have to move up on the stack. So you are continuously minimizing the data which need to go up on any let's say industrial stack. The third, which comes down to the data analytics strategy, and analytics is again, it's a complex world, and I'm just going to simplify. We can put into the 4 categories like analysis, learning, projection or prediction, and optimization. And there's a lot of pre-existing technologies which we have, because this is where, as we mentioned, that one of the purpose of digitization is to leverage what already being achieved in the IT world and leverage it in the industrial world. So we have this line shows basically above things which have been on this line is something which already IT has understood. We have good understanding, good tools, and then below the red line, which we have things which are more emerging, which are newer. And when as a enterprise or industrial architect or industrial solution, you need to be open to leverage what technologies which are already being generated. And this comes back to the creating the structure or digital models upfront, so that you can leverage these kind of technologies which normally worked against the IT environment, and that IT environment was always structured. So that sort of becomes a strategy for analytics, that you don't necessarily always look for unstructured data and then spend 80% of time to cleanse the data, to find the right structures, to find the right relationships before you start getting any outcome of your investment. So this is a little bit a simple use case, just to give a perspective from the both from the data architecture or data strategy and analytics strategy. We see agriculture is one of the most distributed environment, because you have a lot of fields. In the field you have a lot of let's say zones which may have different conditions. Like some zones may have soil moisture at X levels, the one may Y level, different temperatures, different plants, different height of the plants. So like there's a lot of variability when you look into the edges. And then what you want to do when you're trying to do precision agriculture, the whole purpose of precision agriculture is to do a controlled environment, or create a control where you give the water only when it is required, and only give the amount of the water which is required as per the plant condition. Which means that depending upon what crop you have and what's the current stage of the crop against what is the current stage of the plant, then you make a decision how much water is required. And if the soil moisture has less amount than that, then surely you need to open the valve to give the right amount of the water at that particular plant. So very important that it has to start from the edge level computing. So like continuously look into the sensor data, map it into the different models, cleans it there only, and have the local policies. So like, because there's no reason for anybody to make a decision how much water need to be given on a particular zone by bringing all the data of the cloud and then doing all the analytics, because in the edge itself, you know what's the current state of the crop, you know what is the current soil moisture, what is the weather, and take that information to make a decision whether this zone should be wetted or currently it is in the right state. And then going into the next stage, which is more like a gateway, like this is where now you do the aggregation. So because you have multiple zones and you have field, and this level you're now making a decision is the field level decision. So now you're looking into the models which are next level. So like you're looking into the crop models, the analytics models, and you're making a decision which can impact the whole field rather than impacting a specific zone. And those sometimes becomes a constraints which you may want to put at the field level. So like example can be, depending on what crop you have, you may push those constraints all the way to the edges, so that you're not going and manipulating each edge manually. So that's where the gateways come in. And given that you will always have more than one field, you will have different kind of crops in different fields. So the cloud becomes important, where I should be able to see all my crops across my fields. I should be able to optimize how much water is required, how much fertilizer is required, how much pesticide is required, depending upon different conditions which these crops go through year by year, season by season. And hence you need to do the long range learning, as we mentioned earlier, which will be relying heavily on the big data environment. But now your big data is not unstructured anymore. In the big data, you have exactly know what field, what crop, what stage, and what was the pedigree of the fruit or the vegetables was, all the way from the seed to production. So with this, there are a few important things aspects which gets covered, like data management. So like you collect, process, store, forward of the data. That can be on the edges, and it can be on the gateway or in the cloud, but you're doing a different level, because on the edges you have more unstructured information versus when you get to the cloud. Analytics, you are doing analytics on all places. You are doing at the edge level, you're doing at the gateway, you're doing at the cloud level. Monitoring, mostly you do the local monitoring. Again, we don't necessarily always have a need for cloud, because that all depends on what exactly the reachability of the information which you need. In some times, like if I'm going to take a specific example of, let's say, manufacturing plant, you may have everything which is required in the plant itself. So in this case, the cloud becomes more as nice to have, or may not always have. So like in this case, everything can be localized, optimized in the manufacturing plant itself. So same same thing is here. So your monitoring starts from like if I'm only interested in my field, or I'm interested in all the fields which I have across the globe. So like this is where when you go from the server or the local server or gateway to the cloud level. And that's the smart program practice. This is where the as you mentioned, the long range learning comes in, and this is where it's very important that now we start talking about how do I going to collect all the crops pedigree, different conditions across different even farmers, so that learning is fast. We are not learning one crop at a time, but we are learning different crops, different geographies, different conditions, and then trying to see what's the best way to keep them most healthy and create the maximum yield out of the crops, irrespective of external environments, like whether it is less heat, more heat, less rain, more rain. So basically, you know what are the parameters through which you can adjust the things which you cannot control, and that's why it becomes important to do a continuous learning across a big space. So with this, this is my last slide. So what are the takeaways? I'll just go through like a summarization of the presentation. So it starts with the data anatomy. It's very important to understand what kind of data are being produced in the enterprise. And when I say enterprise, we're talking about the industrial perspective. And categorize them in terms of the potential use against time, because just collecting data without understanding what kind of data, what's its use is just a wishful thinking that someday this data is going to be used, and that's basically it says that you follow the data path. Till the data gets consumed, it is useless and should not be necessarily stored and put there, which means that you need to know from source till it becomes it creates its value, and after it creates a value, then it's whether you maintain or not, that becomes a business decision and no more a technological decision or regulatory decision. The second thing is data processing. So understand data quality and formats along with semantical value, like what the value that data is generating, and create a common taxonomy. This is where the just doing the abstraction without having a right taxonomy is not going to create a right level optimization. So give the right taxonomy, give the definitions along with relationships, and innovate on digital models for the enterprise, because these digital models are the one which is going to solve multiple use cases. The digitization is not about one specific use case. So once you have the digitization of, let's say, the manufacturing plant, it may be used for energy efficiency, it may be used for more automation, material optimization. All of that becomes a use cases over the digital models. And not only that, these are digital models which are going to affect the business systems as well. So today's ERP is not going to look the same as we go into the future, which ERPs which are influenced by the digital models. So that's important to create the right taxonomy. It's like an information model, and we have learned from our experience who are coming from IT originally that how important the information models have become in the enterprise. And this is where you have to follow the operation route. Like you have to see what are the operations, what are the sequences, and hence what are the how the semantical values have to be preserved as you move on the operations route. The third, which is data storage. So understand the data use, its frequency, longevity, etc. Store data close to its source and as little as required. So it's not about being fat in the data, as I mentioned earlier, and I think I've talked a lot. It's not about more data. It's about useful data. And useful data only you can do it once you understand where to store and how much to store. So basically, you manage the data trace. And the last but not the least, the data analytics. Understand the outcomes of the analytics in operations and business. So don't just doing machine learning with no outcome or understanding is not necessarily the right investment. So it's good to define the outcomes first, make the projects the ROI based, spread analytics from edge to clouds. Like not every analytics has to sit on the cloud, and some of the analytics may be more appropriate inline, some of them may be offline. And leverage the compute. The compute has become cheaper. The sensors are getting democratized. We need to use those technological barriers which have been removed from us. So like do it as more at towards the edge, and that saves a lot of things. That saves your bandwidth. That saves your management infrastructure. That saves your cloud infrastructure. So that's the more we do in the edge, the more outcomes that you will see. So with that, I'll just, this is my last slide. So I appreciate all of you listening, and let me take a pause and see if there's any question. Yeah, so the question which has been, what are the key product differentiation relevant to buyers and users? So let me try to understand the question here. Maybe I may try to read it differently, and you can recorrect if the question is not understood right. I think it's a product differentiation with respect to developers and users. So the key product differentiations from the I'll say in this case you're talking about different technologies, not necessarily product. Like what are technologies which are differentiated? And I've always put as an industrial, if you don't have a good structure to solve the industrial problem, it's going to be very expensive, and it will not generate the right ROI. So it is important to create the industrial model, and this is where the digital models we're talking, and that's where the developer comes in. The developers are the one, or the architects or developers, they are the one who will understand, like by breaking the boundaries. It's not about this is part of OT and this is part of IT, but it's like in the industrial environment, what are the models, what are the relationships, what are the events which are going to come in, what are the sensors which have to be communicated with, what are the processes they're going to run through. And that's a key. The product has to support that kind of environment where you can generate these models as easy as we have tuned to generate the information models in SQL kind of databases. When it comes to end users, the end users now have to be empowered that these are the end users should be able to change the process rules or policies by themselves. They don't have to go and create a 1-year project and change the whole plant philosophy, which means that they should be able to say, okay, now as per new policy, I'm not going to necessarily maintain the temperature, let's say, for this particular cooling tower for 50 degree, but I will maintain it at 40 degrees centigrade only. So there are different policies that they should be able to set for manually. That's one. The second is that they should be able to tune the analytics to generate the optimization, which means that they should be able to make a decision where they can optimize better, and where they can let developers know where there are areas of improvements which are, you can say, low-hanging fruit or bigger opportunities lie, and let developers create the analytics for those specific areas. So so it means that the product should support a easy way to insert the analytics and override with the knowledge of the people, because the industrial world is not, it's, as I was mentioning earlier, the difference in social media and this is industrial world is still going to be very structured, and it's going to remain as very well executed machine. And hence you will need a lot of analytics will be able to do and will continue to do. And on the same time, people are going to play the role at different levels. Like currently they play a role which is more as an operator, and they will be playing a role which is more a manager, which means that they should be equipped to tune these analytics and processes themselves. Great question. Who are the various persons involved? So we see that currently, and I will take a practical situation here. When you go to, let's say, manufacturing or fabrication plant or refineries, you will see three kind of people there. You will see people who are technicians, like more people who knows how to work with mechanical things and all that. You will see electricians, which is basically taking care of electricity and all that. And then you will see the operators, who are mostly sitting in the control rooms and making a decision on different settings which are required. And then IT normally is less to be seen in those environments. So where we see currently is, first is obviously the IT, given that we are talking about the merging the IT and OT here, the IT has to play the role. So it means that they have to come into the field because they have this is the knowledge which they are bringing in, what they have used in the enterprise side, and hence their involvement is important. But in addition to that, I think we have a role missing in this digitization space, which I'll call digital developer or digital. You can use any role, but somebody who has a multiple, I'll say, hats at this point, but in the future it will become a more a skill set or a role which has to be there in these manufacturing or plants or terminals, who has the knowledge of not only the mechanical or electrical, but it may have knowledge on the compute as well. And that's going to be very important, because we have seen, even if there are a lot of control engineers out there, but control engineers normally are in the design time. When it comes down to the runtime, not their role is very limited, or they're not there. But this digital engineer is somebody who will be you can say a single hat which may have multiple skills. Somebody who understands the compute, understands the how to work with the model-oriented systems, and have a knowledge of mechanical, electrical, and all that. So that's the role which we see. That's going to be a new role which will get defined. But when we see currently, you have the OT people and IT people. They have to come together for a solution. It's not just on the OT, or it's not just on the IT. Thanks a lot. I appreciate again for everybody listening, and will be, if there's any question you have my LinkedIn profile there. Feel free to reach out to me. And this is very interesting field for us. We're currently working with the real people in the industrial world, and we are learning ourselves a lot, and more than happy to share that learning with everybody. Yes, I have heard about car project. That is right, and I think we may not be able to differentiate between car versus what we do in Atomiton. But there are similarities in terms of the models. There are differences when it comes down to keeping those models in sync with the physical environment, because GE is calling digital twin, but I didn't want to use that term, mostly because after giving the term, they have started defining the digital twin the way it is. We don't think that's the right definition, but the concept is right. Like you have to have the models which are in a software environment, but are keeping in sync with the physical environment, and they can have communication both ways. Basically, when the machine changes, your model gets reflected, but when somebody changes the model, it has to turn the machine different. So that's very high level, but more than happy to discuss in detail later.